So, in this lecture we are going to talk about model accuracy with MATLAB case study. We want to consider some comparative case study. So, first we want to recall our continuous time control to output transfer function for synchronous buck converter with sampling delay. We want to consider discrete time control to output transfer function for a synchronous buck converter, and then discrete time and continuous time small signal model, MATLAB coding, and finally small signal model accuracy comparison using MATLAB case study. So, here if you remember our buck converter continuous time control to output transfer function for sample data system. So, we know GVD, and this can be derived from our equivalent circuit model, AC equivalent circuit, and we know in digital control there will be a total loop delay of Ts plus dt. What is Ts? That is the sampling plus computational time, and dt is the dPWM delay. Then the transfer function can be modified by considering the control to output transfer function of the original converter into the delay amount, which is e to the power minus s tau d, and then the control to output transfer function with delay can be considered the same thing with multiplied by delay. And we have discussed this particular model in lecture number 31 in NPTEL in this course, that means digital control in this particular course in lecture number 31. Now, so buck converter discrete time control to output transfer function, that also we have discussed, where we have obtained that xn plus 1 tilde is equal to A equivalent into xn tilde plus B equivalent into D tilde, and output voltage is C equivalent to xn tilde, where A equivalent for a buck converter, if we take low side and the high side MOSFET RDS1 identical, then their on and off matrix are identical. So, you will get e to the power at. Then B equivalent we also know e to the power a into t minus tau d, that is the total delay beyond V into t. So, total loop delay we have discussed, that is the Ts plus dt, and this is the output matrix can be alpha RC in alpha. Now, if we apply Z transform here, and we know that we can derive the discrete time control to output transfer function, which is like this. Now, what is our objective? Our objective, first we want to draw the Bode plot of GVDS without delay, then GVD with delay, because in digital control we have the ADC delay plus dPWM delay, and third, on the same plot we want to plot GVD Z, but Z is an irrational function of omega. So, basically if you use MATLAB, by default it will convert into W domain, which is a kind of a bilinear transformation, that means Z will be replaced by W, so which is a complex number in frequency domain. So, we have discussed this like a discrete time model, small signal modeling in lecture number 38. So, we are not going to repeat. Now, we have considered the synchronous buck converter parameter, which is this, and which we have considered for various other lecture. In fact, we have discussed also lecture number 35 and 36, where we have shown the large signal model validation. So, we have identified our discrete time model is accurate and it can exactly capture the cycle by cycle behavior of the switch simulation. Now, we want to see if we perturb the discrete time model, obtain the small signal discrete time model, it is considered to be very accurate, but it is mathematically somewhat complex because you have exponential term. So, if you see we have this exponential term. So, even if you get this transfer function, you may not have sufficient insight in terms of poles, zeros, but if you go back to the previous expression, you know the poles and zero, these are very well known. There is a Q factor, omega 0, which is a function of in a practical buck converter, it is almost identical to 1 by LC. So, that means we know there is an LC oscillation, like natural undamped natural frequency due to the LC. We also know there is an ESR 0, and we will also know the Q Fermat depends on the load resistance as well as the this parasitic like R1, RL and so on. So, So, that means the previous model gives us insight in terms of poles and zeros, and we have considered in our earlier NPTEL course that means the control and tuning method, that course, that how to design controller. In digital control, before you design the controller, we want to first make an analogy. Can we obtain somewhat simplified version of a digital controller? That means, can we use this continuous time model with delay, and can we compare with actual discrete time model? Because actual discrete time model is very nice, very accurate, but it has less insight in terms of poles and zeros, and that will make us very difficult to design a compensator. So, we want to design first in this course particular lecture, we want to see how closely we can predict the behavior of the digital controller using continuous time model by suitably providing the delay. So, here we have considered this buck converter as the case study, and I am again recollecting the concept. That means, if you take a digital control, I am first considering the controller a simple PID or PI controller or type 2 whatever. Then we have PWM block, and we know for analog control it is simply 1 by Vm, that is 1 by peak voltage, where Vm is the sawtooth voltage, right. This is our Vm from 0 to Vm. Then this delay, we know this delay coming from ADC plus DPWM, and GVD is the continuous time transfer function, and H is the feedback gain. And so, total loop delay, that means if you consider this loop delay K loop under digital control, if you take it is under digital control, it is same as the analog control multiplied by the delay, and the delay is the ADC plus DPWM, and you can get this basic concept, that means how to model the digital controller in this third edition of the fundamental of power electronics, where it introduced that if you add delay, it can reasonably capture small signal behavior. So, we want to check using MATLAB. So, first we will create a .m file, we will again take the buck parameter Vm, we are keeping load resistance to be 1. This duty ratio may not be needed, because if you are using a closed loop control, the R equivalent is the R DCR, this is my DCR plus this is the on state resistance, this is a modulator gain 1 by Vm, and we can introduce a delay 0.1, and this D is needed because we have an additional delay tau D, which is my Ts plus D into T, the dt is the DPWM delay. So, you can see the total delay is the Ts plus dt. So, this is my ADC delay, and this is my DPWM delay. Okay. Then we can define pole alpha, then all these things we have already discussed how to plug in. That means this is the, that means if you go back to our expression of the continuous time, this I am taking as a VE, which is V in by R plus RE by R. Okay. Then these are the Q, W0. So, all this transfer function we have plugged in into MATLAB model. W0 practical, then Q, then after that ESR 0. So, the numerator, if we follow the transfer function, it will be this, denominator will be this, GVD will be this, this is the continuous time control to output transfer function without delay, and the delayed version of that will be the same transfer function, that means the polynomial numerator and denominator with an input delay which is Td, and what is tau d? Tau d is Ts plus dt. Then our control to output transfer function with modulator gain will be Fm into GVD, and delayed version will be Fm into GVD delay. Now, we are plotting first the Bode plot without delay control to output transfer function, with delay control to output transfer function, and these are all continuous time. So, this is our GVC, this is our standard buck converter V0 to D, this one, and then we are adding multiplying with a modulator delay, modulator gain. This is our delayed version, everything is same, only this is coming with a additional delay, that means our GVD delay nothing but GVD into e to the power minus s tau d. Next, we are buck converter discrete time out control to output transformation. So, again the same parameter, everything same Vm. Now, we are using the discrete time small signal model. So, for that this will be derived around the steady state operating condition, and that we are taking the average inductor current and the reference voltage. Next, we are taking on time matrix, off time matrix, and since R1 RDS ones are identical for both low side and high side. So, on and off state matrix are identical, then we will get a B matrix and C matrix. Next, we can compute A equivalent. These are discussed in lecture number, if you follow lecture I think 38, lecture 38 as well as 37. So, you can get discrete time small signal model. So, B equivalent also you can get from there in this course, and then C equivalent is the CM. What is CM? It is nothing but this. So, this is nothing but CM is that alpha RC alpha. Then we will get numerator. Now, since we are this is in the, that means this expression is in the state space form, in the part of state space form, B equivalent into D perturbation, then we have V0 n which is C equivalent into x n tilde plus D equivalent into D tilde. So, D equivalent is 0. So, we can simply use state space to transfer function, and GVDD transfer function we have to specify, that means we got the numerator and denominator by converting state space to transfer function. Since it is in discrete time, so you have to specify the sampling time, that means it will consider to be a discrete time transfer function. Then we have to multiply with our modulator gain and we will use simply Bode plot. This way we are actually getting GVCD in Z domain. So, when you do Bode plot, it will actually plot GVCD in W domain, where Z and W domain they are more or less close for lower frequency approximation. So, they use some Bode in the bilinear transformation, and this is a plot. In this plot, the first one is A, which is this one, which is the discrete time control to output transfer function, and since it is in discrete time, you cannot plot beyond half of the switching frequency. So, this is half of the, because it is the Nyquist frequency range, after that it is invalid. Even for continuous time also it is invalid, because we are applying a pattern averaging technique followed by linearization. So, it require minimum 2 cycle to get the effect. So, that is why all the small signal models are standard averaging, like a conventional state space averaging. The small signal model is valid up to half of the switching frequency. If we consider this line up to this half, you will find the first one is the accurate gain plot, and the blue and the green, that means there is a green and the blue, the gain plot they are identical. So, where the blue one is the continuous time transfer function with delay, and the C, which is the dotted blue line, it is actually a continuous time without delay. Since e to the power s tau d, if we write in terms of j omega, that means e to the power minus j omega tau d, if you take the magnitude, it is 1. So, that means with and without delay, this transfer function and this transfer function gain should be identical, because delay will not alter the gain, that is why they are overlapping. But you can see the effect in the phase. You can see without delay the phase is higher, whereas due to this delay the blue and the green and the red one is the exact discrete time model small signal, that means it is derived, it is a discrete time small signal model which is derived from the discrete time large signal model, and 2 is the continuous time model with delay, and third one with the continuous time model without delay. So, in terms of phase response, the continuous time model with delay more or less capturing that discrete time model. That means, they are more or less close, very close. Only there is a slight difference in gain, but that is fine because that is even close to half of the switching frequency. But typically we design compensator nearly 1/10 switching frequency. That means, if this is our 250 kilohertz, because our 500 kilohertz is our switching frequency. So, 1/10 will come around 50 kilohertz, which means this is our 10 kilohertz, 20, 30, 40, 50. So, that means, if we consider this particular one, so the gain are identical. That means, there is no difference, and the green and red, they are also phase are identical. So, even if you slightly increase this, that means, if you go slightly beyond, gain and phase are perfectly matching for discrete time small signal model and continuous time small signal model with delay. That means, it is reasonable that this transfer function with delay can be used to design digital controller. But the question is, if that is so, then what is the need for discrete time model? And we will show using case study that even though we match small signal model behavior very accurately, closely, but the averaging technique actually loses the information of ripple information. So, I will show you, due to this sampling, there will be subharmonic instability if you try to push the gain when this model cannot capture the subharmonic instability, but discrete time model can perfectly capture. So, we will show that case study in the design case study during the design, but here we want to make sure that as long as they are stable, there is no subharmonic, then you can design the controller, low bandwidth controller, I would say 1/10 or 1/5 of the switching frequency, that kind of control, small signal based controller you can easily design using continuous time model with delay. Okay. So, but actual stability has to be verified with small signal discrete time model. So, that means, in summary, we can design controller using continuous time small signal model, continuous time small signal model, continuous time small signal model with delay, and verify stability using discrete time model. That is the final thing, because the discrete time model, since it retains the ripple information, so you can predict the first scale or the subharmonic instability due to sampling, because in this course I will be showing even for for low duty ratio or even the condition where the analog control is perfectly stable, even if you introduce a sampling delay, that not only causes some deviation in the phase, that means it will degrade slightly phase, but more predominantly it may introduce subharmonic which cannot be captured by this model. So, that is why this model is good in order to design controller, but finally we have to check the stability by this discrete time model. So, in summary, the continuous time control to output transfer function of the synchronous buck converter we have discussed with and without delay. We have discussed discrete time control to output transfer function, and we have compared, we have implemented, I have shown you the step for implementing discrete time as well as the continuous time small signal model and how to obtain Bode plot, and finally I have shown a MATLAB case study to show that up to a small signal bandwidth, that means even up to 1/5 of the switching frequency, the gain and phase can very accurately match with both discrete time small signal model and continuous time small signal model with delay. So, that is why in summary we can say the continuous time small signal model with delay will be a very good solution to start designing the digital controller, because we can get physical insight in terms of poles and zeros, but we will see in the subsequent design class that we need the discrete time model to predict stability. Even we can predict various nonlinear phenomena, or even if you want to do some kind of spectral spreading, the discrete time model is very effective. So, in summary, I think we have understood all the modeling aspect, we have validated using MATLAB, and in the subsequent lecture we will be talking about the design process. That is it for today. Thank you very much.